foremost, I'll do a recap of what we've done so far. After recapping, then we're going to close off this chapter with two more concepts. Second last one will be this concept of sex-linked genes, which is what we're going to look at today. Okay, so far, the topic of inheritance, we looked at how generations of organisms can inherit characteristics. On the surface, when you look at characteristics, we describe them as phenotypes. Okay? Phenotypes are the characteristics. But truly, the thing you inherit from your parents or from one organism to another, we don't exactly inherit the characteristics as the characteristics. What we truly inherit in each cell, we inherit genes, alleles. And that brings us to the word genotypes. Genotypes is what we truly inherit. Okay? It is because of the genotypes that we get our phenotypes. So for example, thank God over the weekend, Minya texted me to say that she got the blood types wrong. So I see every year I confidently say you all likely got it wrong. Okay, so genotypes define your phenotype. For example, if you have a genotype of IO, IB, what is your phenotype? Enter? If you have a genotype of IB, IA, what is your phenotype? Enter? So this is how we play genotype in relation to phenotype. And therefore genotype is nothing more than the combination of alleles. And in looking at the combination of alleles, there's a few vocabulary that can come in very useful to help you describe how the alleles behave and interact with each other. For example, in this scenario here, we have an example where we can say and use the word dominant. Right? This is a dominant allele. At the same time, other words you can use, recessive. Recessive refers to the allele that is masked. On the other hand, blood type is a very good example where we see that other than dominant and recessive behavior, there's one more behavior that you've learned. That has to do with codominance. When you see alleles that are completely dominant over another, this is complete dominance. Okay? So far these are some of the vocabulary we've learned. From dominant, recessive, to co-dominance. The last category of vocabulary has to do with describing the genotypes. Because when you look at genotypes, you can have various kinds of combinations. For example, if we have two of the same kind of alleles, one would describe it as homozygous, recessive, or dominant. So for example, words to use to describe genotypes, you can have heterozygous, you can have homozygous, recessive, or dominant. Okay? Words you can use to describe genotype. You cannot use these words to describe phenotype. Yeah? I am not a heterozygous phenotype. My blood type is AB. My blood type is not heterozygous. Okay? So learn that distinction. These terms are used to describe genotypes. You can use these vocabulary also to describe genotypes. Phenotypes exclusively use it to describe, the characteristics of the organism, from color to eye color to skin color to height, so on and so forth. Okay, blood type. Okay, so this is what we've learned so far. Last week we stopped at the concept of codominance as well as multiple alleles. We learned that although we started off with the simple concept of dominant and recessive alleles, in reality, if you look in the real world, it's not really the case where you only always find two different versions of an allele, one dominant, one recessive. Sometimes, for a particular characteristic, you can find multiple alleles. And a classic example would be blood types. In fact, there are 3 alleles altogether. Whereas what we learned so far, we started off with Mendel's peas and flowers, just 2 alleles. Other than that, we also learned that there's a new kind of interaction. Other than complete dominance, we can have a co-dominance, where if put side by side, both will show. If you understand the concept of co-dominance, then what if I give you this scenario? Let's say I have a cow. Okay? A cow. Cows come in various colors. You have cows that can be red color, of which I do not have red. Okay, let's just label this red. And then you have cows that are just white color. Cows, when you look at cows, their patterns. Actually, they also have exhibit co-dominance when you look at their alleles. For example, notice I'm using the same convention. I'm going to write C, W, C, W, C, R, C, R. I use the same alphabet because it is the same gene. Just that there are different versions of the alleles, and they are co-dominant. Notice for blood types, the alphabet, the base alphabet I use actually is the same. I did not differ from the rule I told you. Same gene, same alphabet. Just that when it comes to co-dominance, we use a capital alphabet to demarcate the allele. Yeah? I don't have like a big I, small I, I don't have a big C or a small c. I just use a capital alphabet. Okay? Notice what we do not do is to write O, A, and B as the symbols for the alleles. If you use 3 different alphabets, you're trying to say that there are 3 different genes. Okay? So this one is not correct. Same here, I do not write the alleles as W or R. This implies that there would have been a recessive version of it. Okay? Instead, I write it this way. This implies that it's co-dominant. That means white and red, co-dominant alleles. So I ask you, if these 2 cows mate with each other, what color will the baby cow be? Okay? What color will this baby cow be? Singapore color. Yeah, Singapore color. Here I was saying red and white. That is the correct answer. It should have patches of red, patches of white. What it should not be, some students shout very loud confidently and then they say pink. Okay? Pink implies that the 2 colors kind of blend with each other. Okay? That is not co-dominance. Co-dominance means that both of them are equally dominating. Both of them will show their trait, just like blood types. Yes?
There's some traits that blend and some traits that don't. So like what determines whether they blend?
Again, mechanisms differ from characteristic to characteristic. Perhaps what I could elaborate is, Shafika asks, are there traits that can blend? Have, but out of the scope. So if you want to learn more, take bio in SH. There is one more interaction you'll learn in SH called incomplete dominance. This means that neither of them will dominate over each other. That means to say, if I say that these 2 alleles are incompletely dominant over each other, then you will get a pink cow. Okay? When red and white are both present, both of them cannot fully show, half show, you get a pink cow. Okay? Okay, but this is out of our scope. Instead, we focus on co-dominance. So this is what a red and white cow looks like. A red and white cow is called a roan-colored cow. So this is what you call it. You call it roan-colored. I'm raising this example to you because when you go to A-levels, you will see this cow example many times. There's some students, when they see the color roan, they don't know what you're talking about. Okay, so roan cow. This is what you always see on the milk cartons, right? It's a bit boring if they just plant one red colored cow or one purely white cow. So they often put these kind of cows, right? So this is roan. That means to say can you tell what the genotype is? You can tell the genotype, right? Just from the phenotype. That means this cow likely has a CW and a CR. Yeah? So I hope you appreciate and enjoy this topic. This topic really has a lot of puzzle solving. Not so much memory work. If there's any memory work you need to do is all this vocabulary. Learn how to use this vocabulary as you justify your puzzles. Yes?
So for codominance you use the suffix. Then for the normal one you use small letter, big letter. What if the first one is like one dominant, one recessive?
Right. Like blood types, right? You see blood types, right? Hoyer's, right? He notices that only A and B are codominant. O is not. Right? Okay. It's okay. If you find a series of multiple alleles, a pair of them are codominant, while one is not, it's okay. You can just adopt the same format and write I and then one capital O on top. I have seen some conventions, some people in other parts of the world, they write it this way. They write IA, ID, then for blood type O, right, they write I. Yeah. I've seen this convention also. But for us, can we adopt this particular convention? Well, a little bit more straightforward. Okay? So how is right? For codominance, we use the same alphabet, capital one, and then there's a suffix. Hey, is this suffix? I don't know what this is. Superscript. Okay, superscript. Okay? But for complete dominance, it will be something like a big A and a small a. Okay? You shouldn't see anything like that. Big A, small a, and then you still got one more small thing on top. No such thing. Okay? If you are going to go codominant, then you're only going to use the capital letter. Okay, I'll pause here a little while for you to recap, summarize before we go into the next section. Yes, you can. Today we're going to look at sex-linked traits. So far, we've been looking at alleles and genes found on the other 22 chromosomes of your body. Actually, your sex chromosomes also come with genes and alleles. I'm going to erase this also. I'd like to bring your attention back to cells. When you look at our cells, each one of our cells comes with 23 pairs of chromosomes. 23 homologous pairs. So something like this. So we have pair number 1, we have pair number 2, homologous pair number 2, homologous pair number 3, and so on and so forth. We should have times 22 of these pairs. And then right at the end, we have either an X and Y chromosome, if you are a boy, or you have 2 X chromosomes if you are a girl. Yeah? But we should have all 22 pairs above. So far, all of the alleles we've been working with, we've been dealing with alleles found on these chromosomes. We call these non-sex chromosomes as autosomal chromosomes. Okay? Sometimes if you see this word pop up, it says autosomal chromosomes. Understand that we are referring to the chromosomes that are non-sex. And so, what does this mean? It means to say all the genetic diagrams you've been drawing so far, we are only looking at pairs of chromosomes at any one time. For example, if we are looking at blood types, we are looking at just a pair of alleles, perhaps this is IO, this one is IB, on just one pair of chromosomes. All the genetic diagrams we've been doing so far you're only just focusing on one pair at any one point in time. When you go to SH side, we'll teach you how to draw genetic diagrams with looking at more chromosomes. But for us, we look at the basics. We just look one pair at a time. And so, if I were to do another question related to eye color maybe, the eye color allele maybe will be found on the third chromosome pair, big B and maybe small b. So every question you've been dealing with so far just focuses on one pair at a time. Now I'm going to introduce to you another category of questions. Sometimes we may give you questions where we don't look at any one of these 22 pairs. Instead, we focus on the sex chromosomes. Because it's very interesting. If you look at the sex chromosomes, I want you to observe the X chromosomes actually is longer than the Y chromosome. This inherently means that all X chromosomes have more DNA. This also means that boys, yes, we have less DNA inherently. Yeah? All of our cells we are short of this much. Okay, missing this much. Yeah? Genetically, we are lacking. Ladies, genetically, you are complete. But this poses a problem because if you think about it, you look at all these DNA, DNA have genes. That means to say, if you look at a boy, if a boy were to have a X chromosome and Y chromosome, he will only have one copy of a particular gene. Whereas over here, he won't have that copy. This poses a very interesting puzzle to solve. If you encounter puzzles relating to sex chromosomes, then it gets very interesting because the boys do not need a recessive does not need a homozygous recessive genotype to be able to show the trait. Think about it now. If a boy were to just have one copy of a recessive allele, it's all it takes for it to show in the phenotype. Girls, however, if you have one copy of the recessive allele on your X chromosome, and you have another one that has a dominant one, actually, if this recessive one is a disease, you can still mask it. But the boys, one will do. And this is a very interesting interaction because what we've taught you so far is this. We keep saying that you must be homozygous recessive for recessive phenotype to show. But when it comes to alleles that are linked to sex chromosomes, it's not the case. Just one copy will do. And therefore, we're going to watch this quick video to show you some diseases that you find that are linked to X chromosomes. And therefore, you often find these diseases more in boys than in girls. Because girls still can just live their lives as a carrier. They carry this disease allele, but on the surface, they are healthy. Okay? Some traits are defined by sex-linked genes. For example, you know colorblindness? Colorblindness is actually a sex-linked trait. So you will find it more in boys than in girls. In my experience of doing all the AA cases, I find it more in boys too than in girls. And this is another disease.
Welcome back to Focal Biology. This week we'll discuss the concept of sex-linked traits, specifically hemophilia. To begin with, remember that every somatic cell in the human body should contain 46 chromosomes or 23 pairs. We get one set of genes from our mother and one set of genes from our father. When paired together, the corresponding chromosomes from each parent are called a homologous pair. One of these 23 chromosome pairs determines the biological sex of the organism. The larger, longer type is called an X chromosome, and the smaller, shorter one is called a Y chromosome. Females have 2 X chromosomes, and males have 1 X and 1 Y. In humans, the female's eggs always contain an X chromosome, but the male's sperm may pass on either an X or a Y. The male determines the sex of the offspring. If he passes on an X chromosome, the resulting offspring will be female. If he passes on a Y, the resulting offspring will be male. The X and Y chromosomes both contain genes that help code for certain traits. Traits that are carried on either of these chromosomes are called sex-linked traits. For instance, instance, the SRY gene on the Y chromosome codes for the development of the testes in males, and the AR gene on the X chromosome codes for male pattern baldness. Hemophilia is a classic example of a recessive X-linked trait. In a healthy individual, the body combats the hemorrhaging process first by constricting vessels to the site of injury. Then a complex series of events called the coagulation cascade activates structures known as platelets. Usually, the platelets interlock to form a plug called a clot, which slows or stops the bleeding. In individuals with hemophilia, however, the coagulation process is disrupted. The platelets either do not mesh tightly enough, or sometimes they will not interlock at all. Untreated, this condition can cause potentially fatal bleeding, even from a very small wound. Individuals with hemophilia are almost exclusively male. So how is it possible that the genes for this condition are carried on the X chromosome rather than the Y? Hemophilia is recessive. Because females have two X chromosomes, receiving one with the mutation would not cause them to develop hemophilia. Their second X chromosome, carrying the dominant healthy gene, would overpower the recessive hemophilia gene. To develop hemophilia, they would need to receive the mutation from both parents, which is highly unlikely, about a 1 in 25 million chance. Men only have one X chromosome, and their Y chromosome can't overshadow the hemophilia gene. If their X chromosome contains the mutation, they will have hemophilia. Despite not actually suffering from the debilitating effects of hemophilia, women with one copy of the gene are carriers for the condition. They are capable of passing it on to their descendants. If they pass the hemophilia gene on to a daughter, the daughter would also become a carrier. If they pass the gene on to a son, he would develop hemophilia. If a carrier woman and a healthy man reproduce, they have a 50% chance of having a daughter who is a carrier for hemophilia, and a 50% chance of having a son who has the actual condition. One of the most famous examples of this happening is in the royal houses of Europe about a century ago. Queen Victoria of England was a carrier for hemophilia. She passed the mutation on to several of her children, and thus on to the royal houses of Germany, Spain, and ultimately Russia. Her granddaughter Alexandra married Tsar Nicholas II of Russia, and their son's hemophilia played a direct role in the downfall of the last Tsar's regime. Okay, that's pretty much it for this week. If you found this video useful, I hope you'll consider subscribing to my channel and leaving some feedback in the comment field. You can also check us out on Facebook, Twitter, and Instagram. Thanks again for watching.
Okay, so new way of writing alleles. So far we've learned a few ways. We learned that if something is dominant over another, we use big caps, small caps. If it's co-dominant, we use the same alphabet, but we can change the superscript. What about sex-linked genes or alleles? If it's linked to the X chromosome, we will write an X, and we will use the superscript, we use either dominant or recessive alphabet. So for example, if we look at hemophilia, maybe I can use big N as the dominant one, small n as the recessive one. Okay? So you see the convention, I'm trying to merge a few things together. The big alphabet represents the chromosome, the small ones on top, superscript, you use it to represent whether it's dominant or recessive, whether it carries the dominant or recessive allele. If it's linked to the Y chromosome, you use a Y, then on top you will write whether it's big N or small n. So let's try an example, let's try a puzzle. What is the probability that a mother with hemophilia will have a son with hemophilia if the father is a healthy one? Okay, can you try? Can you write down the genotypes of the mom and dad first? Without drawing a genetic diagram, you can use the simple square technique if you like to solve this puzzle. What's the probability that the son will have hemophilia? If mom has hemophilia, dad is healthy. Can you write down the genotypes of mom and dad first? everyone should have a square. I'd like to see you practice writing the genotypes for sex-linked genes. What do you realize? It's the probability that you get a son that has hemophilia. Okay, I noticed everyone using slightly different alphabets as a superscript. That is fine. Use big A, small a, big R, small r, big N, small n. Up to you, yeah? I start off a little bit up. So let's say I put mom on top. Here's mom, this is dad. Okay, what is the superscript here? Maybe the question should be, hemophilia, just now they said it's a recessive or dominant disease? Recessive, huh? So if mom has hemophilia, what does it say about mom's genotype? Mom likely has 2 copies of the recessive allele. So I'm going to write, I'm going to use small n. Okay, you can use something else. Small n, small n. Dad is healthy. He only has 1 copy of X chromosome. That means to say, likely, he is dominant. What about the Y? Do I need to put anything on top? Don't need. Because this allele is only found on the X chromosome. So this is how you start off. Okay, then you fill in the blank things. Let's look at all the daughters and all the sons. You would have daughters that are heterozygotes. Yeah. The daughters, no chance of them getting hemophilia. Yeah. Because they will always be masked by the allele provided by the father. Let's look at the sons. What's the probability that sons will have hemophilia? Okay, let's look at son number 1. Small n. Son number 2, small n. Okay? So actually what's the probability? Okay, I guess if you look at grand scheme of things, if the baby haven't come out yet, don't know the gender yet, yeah, you know, you have a 50% chance of getting a son with hemophilia. Now what if the child is already born and they notice that the child that is born is a son? Yeah, then I ask you, this son, what's the probability that the son that has just been born has hemophilia? 100%, right? Okay. What does this mean? It means to say that if you look at a couple like that, a lady with hemophilia, a guy that's healthy, it is 100% certain any boy you get will have hemophilia. So actually these are questions that a couple with hemophilia would have to go through. They will have to think about this. Because it is 100% thing. It is not like, you know, previously when you look at some ratios, it's a 3:1. Here, when it's linked to gender, boys often will show it more if the disease is recessive in nature. So if a mother who is has a recessive dominance, homozygous recessive, no, I assume a lot of questions beyond their mind, whether they want to pass this on to their son also. Yes? Phineas, can a guy be a carrier for hemophilia? So the word carrier implies that, correct. The word carrier means that I'm carrying the allele, I carry the recessive allele, but I don't show the phenotype. In other words, guys cannot be carriers because when they have the recessive allele on their X chromosome, they will still show it. Only females can be carriers in sex-linked diseases if it's X-linked. Okay? Let's try question 1. Color blindness is an X-linked inherited trait. They are telling you it's inherited on the X chromosome. Okay. What is the genotype of a male with color blindness? So which one will you choose? There are 2 layers to choose, yeah? One layer is to choose gender. The other layer will be to choose the combination, the genotype. Okay, which option would be the best option? Okay, we are kind of split between a few answers. Okay, so C is the correct answer. If you look over here, they're asking what's the genotype of male with color blindness? They say color blindness is an X-linked inherited trait. Okay, I think the problem here is that we don't know whether color blindness is recessive or dominant, right? We have not been taught. Okay, let's do quite nice. Color blindness recessive or dominant? Why is it this answer? Let me search. Color blinded X-linked. Is it wrong? Examples of X-linked recessive condition. Okay, so this is not a correct answer. I would think that a better answer would be if this option here has a small n. Yeah? So this is, I mean, if it's a dominant disease, that means even the ladies will get it very often. Yeah? Okay, so this answer is wrong. This should be X and small n on top. That will be the correct genotype of a male with color blindness. Yes. Yeah, please. Do you need to go? Oh, you cannot move. Oh, okay. There you go. It's your worksheet. Okay. Last category of questions that you can encounter. So far, we've been asking you to solve puzzles using genetic diagrams. In the case of humans, you will find another category of questions where we provide you a family tree. Another word for family tree is a pedigree. You are required to be able to analyze family trees or pedigrees to be able to find out what is the genotype or phenotype of individuals. So let's look at this particular pedigree. Can you tell, based on this pedigree, whether this disease is dominant recessive or non-sex chromosomes, or is it linked to sex chromosomes, dominant or recessive? The clue is in how many males and females there are affected. Affected means have the disease. So those shaded in, those are affected. So can you tell? Is it a dominant or recessive? Is it linked to sex chromosomes or is it linked to the non-sex chromosomes? Can you tell? Okay, everyone ready? You choose an answer. Then we'll do a quick run through. Okay, let's see where we predominantly fall. Oh wait, not yet. Yeah, sure, too early. okay, as you try this question out, let me show you one page of your textbook. You can find this page on page 17. Look at page 17 of your textbook. We show you examples of pedigrees and what you will expect to see if it is sex-linked or non-sex-linked. When you look at X-linked recessive diseases, you tend to find that it is the males that tend to have the disease more, probability speaking wise. So if you want to tell if a particular disease is X-linked and is recessive, try to spot such a pedigree. You should see a lot more males in proportion compared to females that have the disease. And it makes a lot of sense when you look at it in context to what males have. They only have one copy of X chromosome. If a disease is not linked to the sex chromosomes, then you'll find that gender doesn't matter. You can find this disease present in males or females in almost equal proportions. You won't find it exclusively in males or females only, or in higher proportions. So we look at this family tree, what you find is that actually I have quite a number of males with it. I have quite a number of females with it as well. Actually it's quite balanced. It means to say gender is not part of this equation. This particular disease is not linked closely to gender. So we can rule out the last two options. It's not linked to gender. If it's not linked to gender, then the next question is this disease recessive in nature or dominant? And how do you tell? Okay, Kara says it's recessive, but what is the giveaway clue that it's recessive? Between 8 and 9. Okay, you all notice this trend so far? To have a baby that's recessive, to have a baby that shows the recessive trait, you need a baby to be homozygous recessive, right? It also implies you need both parents to have one copy of the allele, correct? And one copy is enough. So you look at these two parents, they don't have the disease. Yet, next generation you find one baby with the disease. This most certainly implies that this disease is recessive in nature. If the disease were dominant, then if this fellow over here has a disease, that means to say parents confirm will have one. Because for this baby to inherit one dominant allele, it means that one of the parents will have the dominant allele. Then the parent should have showed the disease also. So, if you want to justify that a disease or something is recessive in nature, try to look for a pair of parents that don't show the trait, and then see if their children show the trait. Because if their children do, then it implies that this disease must be recessive in nature. Okay? B. Let D represent the dominant allele for disease trait, and the small one to represent the recessive allele for the disease trait. State the genotype and phenotype of individual 14. Let's look at individual 14. What is the genotype of individual 14? Can you tell? Okay, we know for a fact it does not have the disease. Okay? So which genotype can we rule out altogether? Double small. We can rule out the homozygous recessive. Confirm cannot be this because no disease. So we are left with heterozygous or homozygous dominant. Yeah? Okay, see? Puzzles are all like that one. It's really use logic, common sense. So what would 14 be? Okay, then Finya, how will you argue? Why do you say this one confirm will have one big one and one small one? Why cannot be both big? Okay, Finya says the fact that this person is healthy means that confirm will have at least one big. Correct? That's a good argument. If it does not show, means confirm I have one copy of the dominant. Okay, so how do you prove that it will have one copy of the recessive? Okay? Finya notices that if you look at the mom has the disease. That means to say, mom would be homozygous recessive. We don't care what that is, but the fact that number 14 is healthy means that number 14 has at least one copy of the big R. Correct? Where did this come from? It has to come only from that. Yeah? I don't care what dad's genotype, the second one is. I don't care. Because the fact is, individual 14 can only inherit this big R from dad. What about the other one? Why am I so confident to say that will definitely inherit from mom? Because mom has no choice. Mom only has 2 copies of small r. Confirm will pass 1 copy to this individual. Okay? So the fact that mom has a disease implies that she has 2 copies, implies that number 14 has no choice, will have to inherit 1 copy as well. Yes, very good. So number 14 you can say is a carrier. Because looks healthy, but she has 1 copy of the allele. And if she were to find a husband who is heterozygous, there's a chance that the child may have the disease. Okay? So as you justify all this, learn to use all the vocabulary you've learned before. For example, you can use words like, oh, this individual is likely to be heterozygous because likely inherited 1 dominant from dad, inherited 1 recessive from mom. We know that mom will likely have to give 1 copy of the recessive allele because mom is homozygous recessive. That's why she shows the recessive phenotype. I'm using all the vocabulary you've used so far. That's the only thing I need you to memorize here. Okay? The vocabulary, the language of biology. Okay? Let's use the remaining time to complete the questions here. I have around 10 minutes. Could I get you to try these questions out? You will encounter 1 question over here, question 2, that now finally requires you to write out your justifications. I'd like you to try to write out your justifications here to see how concise you are, how good you are at using the vocabulary. Okay, and then we will see how much you can go through later on. Most of them can only go through question 1. Okay, but please try this out. Yes, yes. Now you are expected to know color blindness and hemophilia, etc. Is the disease causing dominant or recessive? So usually if you want to explain, actually you can go by the format you use. You can say, I can say that's recessive because then you can make use, you choose parents and children to show. You say, you look at parent so and so, both will show the dominant phenotype, but then the offspring shows the recessive phenotype. That implies that, and then you can go on. So you can quote parents, you can quote the numbers, that's why you provide you the numbers. Yeah. justify your answers? We provided numbers to all the individuals so that you can specifically quote individuals. For example, if you observe two parents coming together resulting in a certain offspring with a certain phenotype, go and quote those numbers as your justification. Okay, before you go off, let me just go through question 1. I see that we are torn between D as well as B. Okay, between D and B. So let's look at the answer. Let's work out this puzzle. Woman is a carrier. That means to say the woman has one copy of the dominant, one copy of the recessive. They say the male is healthy. So that means the male likely has a dominant one, just a single dominant one. Okay, what about the lady's parents? What could the genotype be? They say that both parents are normal. So it provides us a little bit of a clue. Let's look at this lady's father. The lady's father would therefore need to have the dominant allele, right? Because the lady's father is normal. So now let's look at the mom. What about the mom? The fact that this woman has one recessive allele, but it did not come from dad because dad was healthy, means that likely it came from mom. Okay? Likely came from mom. This one therefore likely came from dad. Then what about mom? They say both parents are normal. So mom must have at least one copy of the dominant allele. So these are likely the genotype of the parents. So her father must have been a carrier. Pina brought up a point earlier on. Males cannot be carriers. Mother also possesses the gene. Yes. Mother most likely possesses the recessive allele. Even though she doesn't show it, but she has one copy that masks the other. All daughters will carry recessive gene. Is it possible that all these couple's daughters will carry the recessive gene? I don't know, I'm going to quickly do a quick cross. So if I cross these two together, okay, daughters? No, one have. Next one, the son, one have also. You could have a son that has the disease, but none of the daughters will have the disease. Yeah, all daughters will be quite okay. Except that there's a chance the daughters may be carriers. All of the sons will be hemophiliacs. Not really. It's a 50-50% chance. It could be that the son will have, could be that don't have. Okay? So B is the best answer. Next week, let's go through and have a look at some of the responses. How you justify your puzzles. try to see how concise you can be. Yeah, you can be very long-winded, but actually you can be very concise. For those of you who have already done and submitted, you can see how concise it gets. And really make use of all the vocabulary we've used so far. If you find your justification, you did not use any vocabulary that's genetic in nature, very likely we cannot award you anything. Okay? Try to use the vocabulary as much as possible. Okay, next week I will go through this practice makes progress, and we will end with folder C, which is a very short folder. Okay? And then we are down with one more topic for bio. Y'all never see you. Okay, if not, thank you class.